What if everything you've ever touched, seen, or felt wasn't made of particles at all? What if, at the deepest level of reality, smaller than atoms, smaller than protons, smaller than anything we've ever directly observed, the universe is made of music? Tiny, vibrating strings of energy humming at different frequencies, each note giving rise to a different particle, a different force, a different piece of the world you call real. This is string theory, and it is either the most profound idea in the history of science or the most beautiful dead end ever conceived by the human mind. Today, on Quanta and Cosmos, we're going deep. To understand why string theory exists, we first need to understand the problem it was built to solve. Modern physics rests on two enormous pillars. The first is Einstein's general relativity. It describes gravity, the large-scale structure of the universe, the bending of space-time around massive objects. It is elegant, geometric, and breathtakingly accurate. When we detected gravitational waves in 2015, we were hearing the universe confirm Einstein's math, 100 years after he wrote it. The second pillar is quantum mechanics. It governs the behavior of the very small, atoms, electrons, photons, quarks. It is strange, probabilistic, and wildly successful. Every semiconductor, every laser, every MRI machine runs on quantum mechanical principles. Together, these two theories describe everything we can observe. There's just one problem. They are fundamentally incompatible with each other. When physicists try to apply the rules of quantum mechanics to gravity, when they zoom into the fabric of space-time at the smallest possible scales, the equations don't just break down. They produce infinities, nonsensical answers. The mathematics screams at you. The universe, it seems, is running on two operating systems that refuse to talk to each other. String theory was born as a translator. The story begins not with grand ambitions, but with an accident. In 1968, a young Italian physicist named Gabriele Veneziano was trying to make sense of how hadrons, particles like protons and neutrons, behaved during collisions. He stumbled on a 200-year-old mathematical formula by the mathematician Leonhard Euler and realized it described the data surprisingly well. A few years later, physicists Leonard Susskind, Holger Nielsen, and Yoichiro Nambu figured out why. The formula was describing something physical, the behavior of tiny, one-dimensional strings of energy, vibrating and interacting. Nobody had been looking for strings, they just appeared in the math. And when people started pulling on that thread, the implications were staggering. So what exactly is a string? Picture the smallest thing you can imagine: an electron, a quark, a neutrino. Now go smaller, much, much smaller. A string is a hypothetical one-dimensional object, not a particle, not a point, but a tiny loop or strand of pure energy. Its size is estimated at around the Planck length. That's approximately 10 to the power of negative 35 meters. To put that in perspective, if an atom were the size of the entire observable universe, a string would be roughly the size of a tree. We are talking about scales so small, no human technology can probe them directly, possibly ever. But here is where it gets beautiful. Each string vibrates, and different vibrational modes, different ways the string oscillates, produce different particles. One frequency gives you an electron, another gives you a photon, another gives you a quark. Mass, charge, spin, all the properties we think of as fundamental emerge not from what a particle is, but from how its underlying string vibrates. The universe isn't made of stuff, it's made of songs. Now here's where string theory stops being just poetic and starts being genuinely astonishing. When physicists worked through the mathematics of these vibrating strings, one particular vibrational mode kept showing up, a particle with zero mass and spin of exactly 2. Nobody had put it there, nobody had asked for it. But that exact set of properties is precisely what a graviton, the theoretical carrier of the gravitational force, should have. String theory had, without being asked, produced gravity. For the first time, a single theoretical framework was pointing toward a unification of quantum mechanics and general relativity. The two warring operating systems of the universe might share a common source code. This is why physicists got so excited, and why many still are. But string theory came with demands, strange ones. When you work through the full mathematics to make the theory consistent, to eliminate certain anomalies and infinities, you find that strings can't vibrate in our familiar 4 dimensions of space-time. 3 of space, 1 of time. They need more dimensions. Specifically, the most developed version of string theory, called superstring theory, requires 10 dimensions. The later extension called M-theory requires 11. So where are the extra 6 or 7 dimensions hiding? The leading answer is that they're compactified. curled up into unimaginably tiny geometric shapes at every point in space. These shapes are called Calabi-Yau manifolds, and they are some of the most complex and beautiful objects in all of mathematics. The way those extra dimensions are curled up determines the physical constants of our universe, the mass of the electron, the strength of gravity, the speed of light. Change the geometry, and you get a different universe. Which leads us to one of the most controversial implications of string theory, the landscape. When physicists started mapping out all the possible ways those extra dimensions could be compactified, they found not one solution, but an almost incomprehensible number of them. Estimates suggest there are around 10 to the power of 500 possible configurations. That's a 1 followed by 500 zeros. A number so large it dwarfs the total number of atoms in the observable universe. Each configuration corresponds to a universe with different laws of physics, different constants, different particles, different forces. String theory, it turns out, may not predict our universe specifically. It predicts a vast landscape of possible universes, and we happen to live in one where the numbers are right for stars, planets, chemistry, and life. This is where string theory runs into its deepest controversy. A scientific theory, by most definitions, must make predictions that can be tested and potentially proven wrong. But if string theory allows for 10 to the 500 universes, how do you falsify it? How do you say it's wrong? Critics, including respected physicists like Lee Smolin and Peter Voigt, argue that string theory has drifted from science into something closer to philosophy, a beautiful mathematical structure that may have no connection to physical reality. Supporters fire back. The theory's internal mathematical consistency, its ability to resolve paradoxes in black hole physics, and its tools for understanding quantum field theories have already proven enormously valuable, regardless of whether strings are literally real. And there have been genuine breakthroughs. In 1995, physicist Juan Maldacena discovered something extraordinary, a mathematical equivalence between a string theory in a certain curved space and a quantum field theory on that space's boundary. This is called the AdS-CFT correspondence, and it has become one of the most cited results in theoretical physics. It tells us that gravity in a volume of space is, in some deep sense, equivalent to quantum information on its surface, like a hologram. The three-dimensional world might be encoded on a two-dimensional boundary. This has opened entirely new ways of studying black holes, quantum entanglement, and the nature of space-time itself, even among physicists who aren't sure strings are real. So where does string theory stand today? It remains unconfirmed. No experiment has directly detected a string, an extra dimension, or a supersymmetric partner particle, something string theory in its most popular form predicts should exist. The Large Hadron Collider at CERN has searched, and so far, silence. But the theory is very much alive. Thousands of physicists work within its framework. Its mathematics has transformed our understanding of geometry, black holes, and quantum information. String theory may turn out to be the final theory of everything. It may turn out to be a profound but ultimately wrong path. Or it may be a tool, a mathematical lantern that helps us find the real answer, even if the lantern itself isn't the destination. What it definitely is one of the most ambitious attempts the human mind has ever made to read the universe's source code. And perhaps that's worth something, regardless of how the story ends. The universe is under no obligation to be simple, but it does seem to insist on being beautiful. And in the mathematics of vibrating strings, there is beauty in abundance. I'm your host, and this has been Quanta and Cosmos. If this made you think, share it with someone who deserves to have their mind expanded today. See you in the next one.